Okay, great. Hopefully everyone can see my screen, and thanks for turning out tonight for my geo talk. So today, I'm going to be talking about work that I've been involved with as part of the Prepare project, looking at earthquake hazards in the East African Rift. But first, just to kind of give a bit of background to our project, Prepare, you can see it's quite a contrived acronym. But the point is trying to make that for dealing with natural hazards, the best way of approaching them is to deal with them in advance, as opposed to just reactively dealing with them after they've happened. So preparing for them in advance. And so in terms of looking at earthquake hazards in East Africa, we're a team in the UK based at Cardiff and Bristol University of earth scientists and earthquake engineers. But also importantly, we've been actively involving people in Malawi, where most of our research has so far been focused. So I've highlighted some of the individuals here who have been really key in our project. And it's obviously, by working with them that we can really make a difference on the ground there in how they view earthquakes in Malawi. On top of that, we've also hosted a number of workshops on earthquake risk in Malawi in 2018 and 2019 with so holding classes for students, with local policymakers and with researchers there as well. We've also had some of our visitors in some of our partners in Malawi have also visited the UK to work with us, and we're currently developing an app at the moment to assess school vulnerability in Malawi as well. And so for those of you who are interested, there's a website link here, and we're also on Twitter as well if you want to know more about our project. But without further ado, I'll start talking about the main component of this talk. And so we're talking a lot today about earthquakes, forecasting earthquakes. So it's really worth starting by talking about what is an earthquake and what I mean by forecasting earthquakes. And I'm just going to go straight into it now and just say I'm not talking about predicting earthquakes in terms of being able to say that at this location on this date there is going to be a magnitude 7 earthquake. And it's often held in this, in the media, it's this kind of holy grail of earthquake science, but it's no way we can do it at the moment. And some people would argue that it's not even an attainable scientific goal at all. Instead, when I'm talking about forecasting earthquakes, I'm really just talking about probability. So is there, a 50% chance of an earthquake occurring in this region in the next 100 years? I then talk about why specifically we might be interested in earthquakes in the East African Rift, and kind of a new method we're using to kind of estimate the hazard of these earthquakes using southern Malawi as a case study. Okay, so, from first principles, what is an earthquake? Well, unfortunately, there's not really a simple answer to this kind of fairly simple question, but essentially we think about the Earth's crust being divided by these great big cracks we call faults, which are all kind of moving in response to another due to the movement of tectonic plates. As those plates are kind of jostling and shifting about at millimeters or so a year, then the crust either side of a fault will be moving at these really slow rates, millimeters per year, the rates that your fingernails grow essentially. The faults themselves, however, they won't be moving at this kind of constant velocity because they have some frictional strength. It takes them a bit more for them to move. So we would talk about these faults as being locked scientifically, which is basically, that means they're stuck. They're not moving, even though the plates either side of them are. But although faults have this strength, they don't have an infinite amount of strength. And eventually that movement either side, kind of like bending a ruler, you bend it too much, eventually it's just going to snap and it's going to move very quickly. Fault will move and it will release a lot of energy. And that's the ground shaking that we kind of feel at the surface in terms of releasing seismic waves. And so the energy released in an earthquake, this is huge amounts. So for a magnitude earthquake, it's equivalent to something like 500 million tons of TNT. So for those interested, British Geological Survey have a really great resources explaining about the relationship between faults and earthquakes. From our point of view, what's really interesting is that this energy that's being released, part of it's being released in these seismic waves. And that's the kind of ground shaking you feel at the surface. And this is ground shaking that we can actually record using seismometers. So seismometers essentially consist of two components. You've got one component which is kind of fixed to the ground, so that's going to move during the earthquake. And then you've also got a mass which is hanging, which because of inertia won't move during the earthquake. And so that means that if we can record the relative motion between those two components during the earthquake, you're going to get some kind of squiggles like this. And these are, the classic seismic waves that you'll often see put up on in the media. And they're very, to you, they might look fairly messy, and how can you ever tell anything from it? Well, with enough data from enough earthquakes, you can actually get quite a lot of information. You can get things like the size of an earthquake, and you can get the location of an earthquake. And the idea of measuring earthquakes with seismometers, that's been with us now for 100 years or so. And during this time, we've realized that earthquakes follow some quite kind of profound properties. So one of them is called the Gutenberg-Richter law. And this is basically a way of explaining that there's lots of small earthquakes, but relatively few big ones. And it follows a quite nice mathematical pattern. So that, for example, for every, say you have 100 earthquakes greater than magnitude 5 or above, you would have 10 earthquakes which are magnitude 6 or above, and 1 earthquake which is about magnitude 7 or above. This is quite useful because it essentially means that we can use that kind of Gutenberg-Richter law to maybe forecast about the sizes of earthquakes you might have in a region in future. So for example, let's say you have a region which in the last 100 years has had 5 earthquakes of magnitude 6 or above. Well, then it kind of stands to reason that in the next 100 years, you will also have 5 magnitude 6 or above earthquakes, in which case there's about a 50% probability of at least one of those earthquakes being magnitude 7 or above, or a 5% probability of one of those earthquakes being magnitude 8 or above. So this is what we term probabilistic seismic hazard analysis. We're not saying there will be an earthquake at this location on the 24th of April in 2065. We can't do that, but we can say that given a certain time frame, we can maybe make some prediction about the size of earthquakes that might occur within that time frame. And what's more, if we can start talking about the size and frequency of earthquakes, we can link that to the ground motions that different regions might feel. And that's important from an engineering point of view, because that means we can start making maps like this one in New Zealand, which essentially shows the level of ground shake, the maximum level of ground shaking they expect over a certain time period. In this case, 2,500 years. So we call these probabilistic seismic hazard maps, and they can then get incorporated into your design standards. And so it means that, when you're designing new buildings, theoretically, they should be able to withstand an earthquake within that building's lifespan. So these maps are fairly routinely made now, obviously made for countries like New Zealand, Japan, California, where you have lots of earthquakes and where it's a real risk. In fact, there's even a seismic hazard map for the UK. But before I worry those of you who live in North and South Wales, these levels of ground shaking are tiny. They're about 1/10 of the values that you would be getting in New Zealand, for example. So I really don't worry. I think the UK's got bigger issues to deal with right now. Okay, so that sounds great, right? I mean, earthquakes, we can't predict earthquakes, but we can at least forecast them. But when you look at the kind of, some of the most destructive earthquakes in, say, the last 10 to 15 years, it's quite sobering thoughts for those of us who work in seismic hazard, because really some of them really haven't been anticipated at all by these seismic hazard maps. So if you take the 2008 Wenchuan earthquake, that occurred in a region in China that was assumed to have quite low seismic hazard. If you take the 2011 Tohoku earthquake in Japan, well, we knew that there was a risk of subduction zone earthquakes there, but the size of that earthquake and the size of the tsunami was much bigger than these models predicted. Hence, you had the tsunami actually overtopping the tsunami wall that was meant to keep it out. So this has kind of raised a bit of soul searching in the community. Like, is this just bad luck? Like maybe these are, these are low probability events. Low probability events still occur. Or is this more of a fundamental problem with our science in kind of forecasting earthquake hazards? And you get papers like this with quite provocative titles. And I'm not going to go into the full argument here. There's a lot of strong opinions on either side. But one thing I kind of want to highlight is that if we're just considering, the last 100 years of earthquakes as our main source of forecasting when it might occur in future, I mean, in geology, we're taught not thinking hundreds of years, we're taught of thinking about millions, billions of years of time scale. So is a 100-year record really representative of where earthquakes might occur? So if you take, say, this quite old seismic hazard map for Canada, for example, you're seeing lots of high hazard levels, these kind of bullseye patterns, just where in these regions here where they've experienced earthquakes. But who's to say that actually there may be earthquakes that occur in, say, this region here between the bullseyes, where maybe you've got a fault that's just very low slip rate, or maybe it just has very infrequent big earthquakes. How can we capture that kind of uncertainty in these seismic hazard maps? The classic example of this in what we call these kind of seismic gaps is back in New Zealand. This region here, as you can see, has very few recorded earthquakes, but the geologic data suggests there's a huge fault there with a high risk of earthquakes, which should, and to be fair, is included in their seismic hazard model. This is going to be a particularly big problem for those kind of plate boundaries that are moving relatively slowly, because just inherently we have very few earthquakes. Okay, so this is where we're going to kind of bring in the East African rift now, but first to kind of explain what is the rift, why we're interested in it. This is a fairly interesting kind of plate boundary running through Eastern Africa, where the plates, the Nubia plate and the Somalia plate, are moving apart. It runs from kind of Ethiopia here in the north, where essentially it's starting to form a new ocean. Essentially, you're getting oceanic crust forming now. Down the rift goes down into Kenya. In the west, it goes through the Uganda, DRC, Tanzania, and down into Malawi. And we know that the rift has hosted some quite big earthquakes in the past, up to about magnitude 7.4. But what's quite interesting about the rift, maybe from more of a societal point of view, is that the seismic risk in the East African rift is increasing quite quickly. So what I mean by this is there's a kind of a subtle difference between hazard and risk. Hazard is just a natural event that has a potential to cause loss. But if you think about it, a magnitude 8 earthquake in Antarctica, it's not really going to do much apart from maybe to a few penguins. What's also important in terms of thinking about the loss or the risk that might be associated with a natural disaster is also the exposure. So how many people will maybe experience an earthquake, and the vulnerability. So what is the quality of the kind of building stock in that region? So if you consider these two components of risk, well, exposure, well, population in the rift is already quite densely populated, but that population is expected to grow quite a lot in the forthcoming decades. In terms of vulnerability, well, it's fair to say that the buildings there are not really designed to any code at all to withstand earthquakes. There's a lot of informal construction. So this means that even a relatively small earthquake has the potential there to cause quite significant damage in the rift. So it's important that we're able to constrain this hazard part of it robustly. So obviously this is not something new. People have known about this problem with seismic hazard in the rift, and there's a lot of good work that has gone into constraining the hazard and making these kind of seismic hazard maps for the rift. Problem with that is that it's really just considering the instrumental record earthquakes, as I said, and that record in East Africa is particularly short because there's very few seismometers in the rift. They're expensive and quite time consuming to install. And also, if you think about what I was saying before, the rift itself is quite slow. It's extending about 1 to 6 millimeters a year, we think. So it means inherently there's also quite few earthquakes in the rift anyway. So this kind of leading us to think about, well, maybe if we're wanting to understand earthquake hazards in the rift, maybe we need to think of a different way of approaching this problem. So now I'm going to really be focusing on our work down here in southern Malawi, and kind of going back to the first principles about thinking about what's happening in an earthquake. So as I said, there's obviously a lot of energy being released as that fault finally becomes unstuck and slips. But the other thing to think about is that it's also going to cause the ground to move as well. And in somewhere like East Africa, where that crust is being slowly pulled apart, it kind of causes this downward movement, and it's going to leave kind of a scar in the landscape that we would call a fault scarp. So if we can identify these kind of fault scarps, these are geological indicators of past earthquakes in the rift, maybe we can use these to kind of start thinking about hazard in the rift instead. So can we find fault scarps in Malawi? Well, yes. So this is work we've been doing from field evidence. So we've had 2 field campaigns in Malawi in 2018 and 2019. Obviously, plans to go this year were kind of scuppered for quite obvious reasons. Hopefully, there's a potential we can go back next year as well, seeing if things improve over the next few months. But even without the field work, we've been able to use what's called digital elevation models as well. So this is satellite-derived data where they're basically imaging the surface of the ground in incredibly high accuracy. So the resolution of these models is about 12 meters in a horizontal way, and vertically, the elevation of the ground is correct to within about 0.5 meters. And what you can see here, so this is a kind of an oblique view in one of these models. So you can see this kind of line here. This is about 10 meters high when we've measured it, running along continuously through Malawi for about 50 kilometers or so. And this we would probably interpret as a fault scarp, as one of these kind of geological indicators of maybe a big earthquake that's happened in Malawi in the past. We probably just haven't seen in the instrumental record yet because it's too short. So what we've done in Malawi is actually just kind of for the first time actually systematically map all these fault scarps. And this is the map that we've produced here. And what's really interesting, what's really useful with mapping these faults is actually their length is actually quite useful, because when people have kind of correlated fault length before with earthquake magnitude, you can see there's quite a nice relationship. So for example, if I know that there's a fault about 100 kilometers long, that probably formed in an earthquake of about magnitude 7.2. So essentially using this fault map, we can get an idea of the magnitude of earthquakes in Malawi. But what about earthquake frequency? Well, this is where I should say that this idea of kind of using faults and seismic hazard, that's been done quite a lot before. That's not new, what we're doing. What is new is this idea of working out how frequently these faults might slip in earthquakes. So the kind of conventional way of doing this is visiting these faults in the field and finding material like this that you might interpret as being deposited during past earthquakes when you get a lot of landslides, for example, and you might get a lot of boulders being deposited. And if you can get material from that, from these boulders or material that you can directly relate to past earthquakes, you can use techniques such as carbon dating to date them, and you can get an idea about how often these faults might host earthquakes. And you could potentially do this in Malawi, but this is, as I hope maybe you can appreciate, it's quite a time-intensive process to do it for 20 faults, and it's also, these dating techniques are not cheap. So, in the context of a 3-year research project, there's no way we could apply this kind of framework to all the faults that we've mapped in southern Malawi. So we've kind of come up with a new approach of obtaining kind of slip rates of faults and earthquake frequency in Malawi. And there's kind of 2 stages to this process. The first one is to kind of get a better understanding of how quickly the tectonic plates in Malawi are moving with respect to one another. So the way we do this is using GPS data. So since about 2016, we've created a network of about 14 GPS stations in southern Malawi, which are shown by the black dots here. And essentially what we do is we've been going there each year, and we install one of our GPS stations in that site. We leave it running for about 3 to 10 days, come back, pick it up. And doing this every year, what we essentially can determine is how these plates have been moving, how these different stations have been moving with respect to one another over that time period. And that can give us an idea of the kind of plate movement during that period. Essentially what we're doing is, if I go back to that slide at that beginning, when I was showing kind of the idea of earthquakes and faults, we're measuring this part here where the faults aren't moving, but the crust either side is. That's essentially what we're measuring with this GPS data. And we're finding that the plates are moving about 1 to 3 millimeters a year. And that is, I mean, you often think about tectonic plates moving quite slowly, but this is even slow by tectonic plate standards. So, you know, if you think about tectonic plate boundaries in the Pacific, they're moving up to about 10 to 100 millimeters a year. So potentially, you know, 10 to 100 times faster than they're moving in East Africa. Okay, so how do we go from this idea about how fast the tectonic plates are moving to how often individual faults host earthquakes? And the way we've kind of developed to do this is to think about, well, what we can say about the rift is, if I take one section of it here, which is shown in this plot here, if you look at the kind of this height of those fault scarps, which is obviously kind of indicative of how big earthquakes they're hosting or how quickly the faults are slipping, and you just look at the kind of the topography, which itself is kind of a record of kind of the long-term extension in the rift where it's been localized, you can see that most of this extension, most of the big fault scarps are kind of on the edge of a rift and what we call the border faults. So essentially what it seems to suggest is that the fastest slipping faults in this section of the rift seem to be at its edge. And that's consistent with what we see in elsewhere in the East African rift and also in other continental rifts. So that's suggesting that these are the faults which are slipping fast. They're probably the dangerous faults from a maybe seismic hazard point of view. Whereas the faults in the middle of a rift probably slipping a little bit slower. Okay, so we can put some numbers behind this now, essentially. So we're saying that there's 1 to 3 millimeters a year of extension across the rift. Maybe 50 to 90% of it is likely to be on these faults at the edge. And so from that, we can get an idea of the fault slip rate as opposed to just the plate boundary slip rate. But if you think about what we're talking about, earthquakes and the faults kind of stick, slip, they don't gradually move like this. They kind of move incrementally, where they're stationary for long periods of time and then they suddenly move in an earthquake. Stationary for a long period of time, suddenly move in an earthquake. So what we really want is this parameter here, what we're calling the recurrence interval, the time between earthquakes. But if we know its slip rate, and if we know how much it slips in an earthquake, which we can get based on its fault length and using these kind of empirically derived scaling laws, then we can get an idea of maybe actually how often it slips in an earthquake. So for example, if you have a fault which is slipping at 1 millimeter a year, and we can work out that it slips 1 meter in that earthquake, then we can maybe say that, well, it's probably going to have an earthquake about once every 1,000 years. So we can basically put all that information together into these kind of seismic hazard maps, where we're saying faults in Malawi are having slip rates around about 0.1 to 2 millimeters a year, hosting big earthquakes, but quite rarely. And this is the hazard map that we've produced, which you can see compared to previous maps. This is from the global earthquake model, is quite different. We've been able to show here that in southern Malawi here, the hazard is pretty much uniform. So this is basically showing the level of ground shaking that they anticipate in the next 500 years. Essentially just a uniform estimate across all of Malawi, using past seismicity as your only indicator. Whereas here, the red lines are showing the faults, and essentially these higher values here are showing the ground shaking we're anticipating, getting much higher values, and also kind of localizing it onto the faults. So we would argue that these are kind of better indicator of seismic hazard in the rift. But these are very preliminary estimates, very liable to change. Please don't take this as our final seismic hazard map for Malawi. There's also some other problems with the approach that we've got in terms of the uncertainties in the GPS data is quite big. We've not really considered that earthquakes can actually, a lot of research showing at the moment, if you have an earthquake on one fault, it can actually potentially trigger an earthquake on maybe an adjacent fault, or alternatively, can actually make an earthquake on an adjacent fault less likely. So there's kind of a time dependence on seismic hazard that we've not really considered in our maps. You could also have a case, as quite famously happened in New Zealand a few years ago in the Kaikoura earthquake, where you don't have one fault rupturing, but you have up to, in this case, 20 faults rupturing, which is pretty surprising to us all. And that can maybe change our estimate on earthquake sizes in Malawi. And finally, we're kind of assuming we've mapped all the faults in Malawi. There's good reason to think that might not be the case if, for example, the faults don't slip to the surface, or the evidence, that scarp, that geological evidence might have been eroded away. So again, going back to New Zealand, there's quite a famous example in 2010 in the Darfield earthquake, where you had a fault that previously hadn't been mapped. So this is after the earthquake, but before the earthquake, that was just a normal field. There was no way of knowing that there was a fault there. Okay, so just to kind of summarize, we can't predict specific earthquakes, but we can give probabilities. In southern Malawi, we've kind of developed a new way of going about this process, and we're anticipating that this region experiences fairly infrequent but quite large magnitude earthquakes. From a scientific point, it's quite interesting, but from a societal point, it's really important, because this region here I'm showing is home to about 8 million people, and that population is going to grow fast in the next decades. So, even a magnitude 6 earthquake there could do a real lot of damage. As our earthquake engineers, colleagues like to remind us, though, it's not earthquakes that really, cause the loss, it's buildings. So there's a real need in this region to develop low-cost, seismically resilient buildings. So, I'll just, finish off just by saying that, within our Prepare project, I think we've made a much better understanding of seismic hazard in Malawi. And if there's any research funders listening, there's still a lot more work to do. And I'll leave it there because I suspect I'm probably out of time.
Thanks a lot, Jack, for this very interesting talk. A lot of really interesting ideas in there. It was really interesting to me, at least. So we've already got a few questions that we can start looking at. So perhaps, Paul, if you could just confirm, I think what you mean by RF power. I think it's probably reflectance, but that would probably be useful to both Jack and myself. There is another question by an anonymous attendee. So how do you anchor GPS stations to bedrock? And is there torsion?
Yeah, that's a great question.
So surface or soil differential movement? Is there any relation to thermal movement?
Yeah, those are all great questions. So when we make this when we select GPS stations, the first thing we do is it's always on hard bedrock. So we are looking for, it's actually quite interesting to find them. It can be really difficult to find them sometimes, but we always make sure we're not on soil or something that might change year on year. And then essentially within that bedrock, we'll drill a hole about 10 centimeters deep or so. And that's how you anchor the GPS station to that bedrock, so we can get that position really accurately. In terms of the thermal movements, yep, that is something that we do see in our data. I'm not an expert on processing GPS data. This is mainly my colleagues who do this, but they assure me that because it's a regular cycle, the thermal movement between the day and night, that's something that you can account for. The other thing we also have to account for actually is each year, during the year, the ground will move with the water cycle during the wet season and dry seasons. And so we always make sure it's at the same time of year as well.
Thanks a lot. Yeah, I was wondering, actually, do you have any problem of having your GPS stations in relatively safe locations, or how do you get?
Yeah, that's another. That was also we considered when we select our sites. So we tend to select sites like hospitals and schools, which are public sites, which we know are going to be there for quite a long term. And then typically we'll actually employ a local just to keep an eye on it. So they'll just go there like a few times a day, who just walking past. Like, so if we're like, a lot of the buildings are like hospitals and schools, they tend to have security guards anyway. So we would typically just give them a little bit of extra cash just to make sure our GPS stations are secure. And we haven't had any issues so far because they use solar panels, which are very lucrative in Malawi, but happy to say that we've not had any issues like that so far.
Yeah, fingers crossed. Yeah, it's better this way. There is another question which is a bit technical, and it came in several iterations. So I'm going to try to convey the question in a relatively simple way. It's from Paul. So it's about I think the reflective or reflectance power at ground level of the LiDAR technique. So I think you were mentioning the use of satellites to determine the topography. And what is the technique using a lot of energy? Is this potentially dangerous for people? What is the effect, I guess, in the environment?
Those are questions I'm probably not the best person to answer. I look at this data after it's been processed. In terms of, so this isn't LiDAR, so this isn't, it's not airborne LiDAR, at least anyway. This is all from satellite data. And in terms of the inference of the return signal, I'm not sure how they process it, but I mean, all the faults that we've mapped, we've essentially ground truthed as well from our fieldwork. So we're reasonably confident that these remote observations we're making are robust.
Yeah, fair enough. Unfortunately, I've got a very limited background in the radar waves as well, so I think we'll have to live with this answer. But yeah, cool. Thank you for trying. Another question is coming from another anonymous or possibly similar, same anonymous attendee. In a faulted region, how do we know that bedrock is actually anchored to the main system?
So actually, typically, a lot of our sites are kind of on the edge of a rift. If I kind of go, I go back can we go back a few slides? I'm still screen sharing, aren't I?
Yeah, sure. Yeah, I think so. I can see it anyway, so probably other attendees as well.
So if you see, a lot of our sites tend to be on the edge of a rift. So they're not directly affected by any fault movement, and these sites tend to be on kind of strong metamorphic basement rock, which is the kind of bedrock geology on the edge of a rift. As you can see, we do have a few sites in the middle of a rift. That basically took a lot of finding. You can, within error, you can do sites which may be just big boulders. Again, I'm not an expert on geodesy and GPS campaigns, but you know, and if there was noise from a boulder that had moved during the between our campaigns, then that would be something we'd be able to pick up and correct for as well. I should also say that as well as these GPS stations, we're also incorporating, there is other kind of GPS data across the East African Rift we're also incorporating into our analysis. And importantly, there's also continuous stations. So these are ones which are just continually left in the ground and continually recording their position over time as well.
Great, thank you. I don't think we've got another question coming through the question and answer panel. Paul is just really astonished by the technology, and I agree, like how do you actually use radar waves to calculate the topography. It's also astonishing because you can measure the altitude without the effect of vegetation. So actually using that same technique, you can do a lot of funky stuff in the tropical environment. And I think there was a very kind of unexpected discovery by archaeologists a few years ago in Central America, where they found actually lost cities in the middle of the jungle. So pre-Columbian cities, just because they were using that technique. So it's really cool. But perhaps to come back to the topic that Jack was talking about, I don't know, Jack, if you could show your Gutenberg, Richter, or Richter, I think you would say in German, curve, the very first one.
Yeah, this one.
Why do you get such an amazing correlation?
Well, yeah, I mean, well, there's a lot of systems in nature follow these kind of what we call power law distributions, right? I mean, one idea is that if you look at fault lengths, they also tend to follow a power size. So fault lengths follow a similar kind of distribution in terms of their length and their the cumulative frequency. So we have lots of small faults, very few big faults. So if you were to say that faults on average slip at the same rate, then that might be one way of doing it. But I mean, yeah, nature can be very weird sometimes, and just following these really beautiful mathematical patterns, which least makes our lives a little bit easier, I guess.
Yeah, fantastic. So actually, this is something that's well documented, but we still don't have a very clear understanding of potentially underlying processes, right?
Yeah, I mean, the physics of earthquakes, we are still kind of straw in the wind, right? We're still, grappling with quite basic questions when it comes to earthquake physics, but it's a very young science. It's only, in the last 50, 100 years, we've really got just a basic conceptual understanding of what's going on during an earthquake.
Yeah, brilliant. Thanks a lot. Don't know if there is any other question. Yeah, I think you've got potentially a very motivated field assistant. So Paul, if you want to help Jack in his research, I think the best way to do it.
If you look up, it's from a German space agency, we get this data. So if you look up Tandem X is its name, if you look up them on Google, I'm sure you'll find out much more about it than I could ever say.
Yeah, brilliant. Great. So I think this is all for today, unless there are other questions, but I don't think they're coming through. So yeah, thanks a lot, Jack, for that very interesting talk. I thought that was really neat and definitely interesting. I've learned quite a few things here. So for the audience, so we're going to continue for one last week the webinars. So next week we're going to have Professor Chris MacLeod talking about plate tectonics and whether we've got everything wrong. So this is quite, I think, a very fundamental question. Yes, so remember as well, next week we don't have the webinar on Wednesday. It's going to be on Thursday, but it's the same time and the same system that we've used until now. And as usual, if you've missed some of the previous talks, feel free to have a look at our YouTube video channel. And so I think that's all for me today. Thanks again, Jack, for that interesting talk. Thank you all for your attendance. And so it's goodbye from me, and I hope to see you next week. Goodbye.
Bye, everyone.